So we will continue today working on the chapter of moment of forces. Last time we have seen how to find the moment vector about any axis. And we worked on couples of moments also. Okay? And we did this example. Now we will do another example on how to determine the resultant couple of different forces. So we have here in this figure, we want to determine the resultant of the two couples shown below. You have two couples of forces, 20 Newton and 30 Newton. And you want to find for each one what is the couple, and then you should do the summation because they want you to find the resultant of the two couples. So if I take now for the first couple, okay, I have a force of 30 Newton parallel to Z and an opposite force of 30 Newton also parallel to Z. And as you can see, these two forces are in plane YZ. Because these two forces are in plane YZ, they will produce a moment about which axis?
X.
Very good, x-axis. If you do the right-hand rule, can you tell me if the moment is positive or negative?
It's in the clockwise direction. It's negative.
Okay, it's negative, very good. Because look, if you try to turn your right hand from the upward 30 Newton force towards the lower one, your thumb will be directed along negative x direction. Okay, so the couple is negative. So here, if you want, it's true that we are in 3D, but because the forces are too simple, you can use the 2D method. Okay, so you can say the distance separating the two forces is what? The perpendicular distance is 450. So I know the perpendicular distance between the two. And from the right-hand rule, I know that the direction is along negative x. So for this couple, I can say directly, I can use the conventional method that I use in 2D and say that the moment is equal to 30. Now, if you want the result in Newton meter, you will convert the dimension in millimeter to meter. So 30 times 0.45 along minus I. Okay, and the result is in Newton meter. Now, we will see that for the second couple is a little bit more tricky. Okay, if you take the second couple, you have two forces of 20 Newton that are parallel to x-axis, but you don't have, these two forces are not in a known plane. It's not xy or xz or yz. No, you have a certain inclination. Why? Because if you look at vector ED, it's an inclined vector. It has components along y and z. Okay, so for this couple, it's not as easy as the previous one. You can do two methods for this couple. We will do first the vectorial, which I found easier in 3 dimensions, or we can do the analysis about moment about each axis. So let us do the first method, which is the vectorial method. If I consider the vectorial method, I should do R vectorial F, if you remember, okay? And when I have a couple, I will take R from one force to the other. So here, for example, I can take ED vectorial, this force of 20 Newton. So when I go from E to D, I will do vectorial plus 20I. If I go from D to E, if I do DE, I do vectorial minus 20I. So when I do R vectorial F, it's equal to ED vectorial my force. Okay. Now to find vector ED, I should find coordinates of points E and D. So let us start by point E. Point E is on which axis? It's on Z axis, and its coordinates are 0, 0, 0.175. Okay, this is for E. Now for point D, D is in YZ plane. Okay, so x of D is 0, and you have that Z is positive. It's equal to 175 plus 300, so 475. And along Y, it's negative. It's equal to 225. So in meter, it is minus 0.225. And along Z, it's plus 0.475. Okay? So now, if I go back to my expression here, I can replace vector ED by, I have 0 along I, along J, I have minus 0.225, and along K, I have plus 0.3. So plus 0.3K, plus 0.3K. Okay, and now I can do vectorial my force. My force is along I, so it's vectorial 20I. Now, if you do the expansion, J vectorial I, it's negative, but already you have a minus, so you get equal to plus 20 times 0.225 along K, okay? And K vectorial I is plus J, so plus 6 if you want, 20 times 0.3 plus 6J. So as you can see here, you got, when you did the vectorial product, you got that your moment has two components, one along K, one along J, okay? Now, if you want to use, if you don't want to use the vectorial product, okay, you want to use the classical method, you should decompose your moment into three. You will say, I will find moment about X, moment about Y, and moment about Z. First, do you have a moment about X?
No, because it's parallel.
Okay, very good. We don't have a moment about X. So as expected here also in our vectorial app, we got a moment equal to 0. Okay, now the next step is to find the moment along Y. If you want to find the moment along Y of your couple, this is your Y axis, okay? If you look at your figure, you have, for the first force, it's passing by Y. So it will not, sorry, it's passing by Z, I mean, okay? This force will not have a moment about Z, but it will have a moment about Y. What is the moment of this force about Y? First, you should take which distance? This one, which is 175. And if you do the right-hand rule, it's doing a negative moment, because if you rotate, your thumb will be directed downward. So for the first force here, its moment about Y is, so if I want to calculate the moment about Y, first I have for the first force, it's minus 0.175 times 20. And for your second force, this one, when you take this one, okay, and you do the right-hand rule, it will produce a positive moment along Y. And you should multiply by which distance? By 475. So you get plus 0.475 times 20. So if you compare with your previous result, you will get the same answer along Y. Okay, along Y, it's 0.3 times 20 equal to 6. Okay, so my, this is how we find my. If you want to find moment about Z of the couple, also we should add the moment of the two forces. As we said, for the first one, no moment about Z. Okay, and for the second one, this one, if you want to find the moment about Z, which distance you should take?
.225.
Yes, 0.225. And if you do the right hand rule, how is the direction, positive or negative?
Positive.
Positive. So also we got the same result that along Z we have plus 20 times 0.225. But as you can see here, the vectorial method is much easier. In one step, you directly get your resultant moment. If you want to use the conventional 2D method, you should take first moment about Y, moment about Z, and moment about X. Okay? Any question for this? Now, once you find moment about moment of the two couples, now you say that the resultant moment, M resultant, is equal to moment vector 1 plus moment vector 2 equals to, you have here, for this one, it's negative along I, so it's minus 30 times 0.45 I. And for the second moment, you have plus 6J and plus 20 times 0.225K. This is your resultant moment. As you can see, your resultant moment has components along I, J, and K. Okay? So any question on this before we move to another problem? Okay. Now, here, in this case, now we will explain what is equivalent forces. Okay? If you have a certain system of forces, you can replace it by one force in a way that the two systems are equivalent. We will see how. Okay? So first, if you consider the following figure. First, I have a force applied on AB. It's perpendicular to AB, and it's at a distance of 250 millimeters from point B. In this system, what is the moment of my force about B? It's F times the distance AB. Okay, so I can say that for this system, F resultant, the resultant force is minus F along J. And for the couple, the resulting moment, I can choose any point. I will choose moment about B. So resulting moment about B of this force is equal to BA times F. Okay. Now it's along the positive or negative direction. If I do the right hand rule, it's turning here clockwise, so it's along negative K. So I put minus BA times F along K. Now for this figure here, the moment about, the resulting moment about point A is what? What is the resulting moment about A? Your force is passing by A. Can it produce a moment about A?
No.
No, so you have 0. Okay? So the moment about A is 0. Now, if I want to move my force F, if I want to move it from A to B and still have equivalent system, the condition is that if I move it, I should add a couple in a way to have my system equivalent. What do I mean by equivalent? It will have the same resultant force and it will produce the same resultant moment about any point. So here, if I decide to move my force F towards point B, I should add a couple. Why I should add a couple? Because if I put my force at B, the force will produce a moment about B.
No, it won't.
No, no, it will not. Okay, so in order to have the same system, what should I add? I should add a couple, okay, that is equal to the resulting moment of F about B, because I want that my two systems should be equivalent. So that they should produce the same effect. Since I moved the force, I should add its moment about point B. So a general rule, when you move a force from one point to the other, in order to obtain equivalent systems, you should add the moment of the force created about the point. Okay? Because when I put my force in B, it will not be able to produce any moment about B. And in my initial system, it has a moment equal to MRB. It was a clockwise moment, and its magnitude was BA times F. This is why here I will put a clockwise moment of magnitude 250 times F. And if you want, we can verify together that the moment about A will remain 0. Because here, if I do the moment about A, M resultant about A, what do I get? If you want to find moment about a point, and you have forces and couples, what do? You add the couples plus the moment of the forces. Okay? So when I take moment about A, I should take the couple, because as we said, if you remember, the couple is a free vector. So if I have a resulting moment couple at B equal to 200 times F, it will, along A, it will have the same effect, which is 250 times F in the clockwise direction. So let us take the clockwise if you want, or if you take the counterclockwise as positive. So considering now that in this equation, the counterclockwise direction is positive. Okay. Since this couple is in the clockwise, then it is negative. So I will put minus 250 times F. Now, what about the moment of force F? What is the moment created by force F about A? If you take the figure here, and this is point A, F is trying to rotate in the counterclockwise direction about A. And the magnitude of the moment is F times the distance AB. Okay? So if you do F times AB, you get the moment of F about A, and it is in the counterclockwise direction, so it's positive. So I will do here plus 250 times F. And as expected, I will get 0, because these two systems are equivalent, so they should produce the same moment about any point. Okay? Any question on this? Okay.
Doctor,
I'm not understanding how at A it's giving you 0.
Okay. Look, at A, this is A here. Okay? When you want to do the sum of moment about A, you should take the effect of the couple. So you have this couple, okay? And you have the moment of the force. The couple, we say that the couple is a free vector. So if you have a moment acting at B, it will be the same moment acting at A. So when you do sum of moment about A, you should take into consideration this couple, okay? This couple is in the clockwise direction equal to 250 times F. Now, for the force F, what is the moment it's producing about A? It's F times D as magnitude, and as direction, it's in the counterclockwise direction. So you can see here that the couple has the opposite effect of the force moment on point A, because the force is trying to create a moment in the counterclockwise direction equal to F times D, while the couple is acting in the clockwise direction and producing a moment of 250 times F. Okay? If you
Okay, thank you.
Okay. If you want also to understand better, a couple can be replaced by two forces, yes or no? So this couple, if you want, you can replace it by the following forces. One that is up here, and one that is down here. Okay? Sorry, the opposite. Because, yes, you want to have a clockwise couple, so yes, it is as I did it. So you want a clockwise couple, so you can replace by an upward force here and a downward force here. Okay, and now you can remove your couple. You have these two forces are creating a couple equal to 250 times d, because I will put the force here. This is 250 and this is 250. Okay, so these two forces can replace the couple, because the distance between them is sorry, the distance is 250 and the force is F. So here you have 250 is the distance between the two. Okay, and the force is in magnitude equal to what? You choose a force equal to F in magnitude. So what will happen here? You can replace this couple by these two forces. Now, if you look at your figure, F, you have here F downward and here F upward. These two will cancel each other. So you end up with the previous system that you have a only force at A, which is the case here. Okay, and this force can only produce cannot produce a moment about A. So the moment of this system about A is 0. Okay, because the couple is simply two opposing forces, and if you put the two opposing forces, these two will cancel out, and you end up with one force at A which cannot produce a moment. And you can see this was your initial system here. Okay. Any question on this? Okay. Now, so what we can deduce, if we want to move a force from point A to point O, this requires creating an additional moment couple. Since this new moment couple is a free vector, it can be applied at any point of the body. So here we are repeating our conclusion. When we move one force from one point to the other, we should add its couple about the point to have equivalent system. Okay, now whenever you have a couple, even if it's applied at B, if you do sum of moment about A, you should take it into account, because the couple is a free vector, so wherever you put it, it will give the same effect. Because if you remember last time, you have seen that if we have two forces, if we do sum of moment of these two forces about any point in the space, we still get the same result. This is why when we have a couple and we do sum of moment about any point in the space, we will have that the moment of this couple about the point is equal to the couple. While for the force, the moment of the force about a point depends on the location of the force, because we should do the force times the distance. So, for example here, if you consider this body, okay, this body is subjected to several forces. It's subjected to force F1, to force F2, and to a moment vector. Okay. Now, if you want to find the resultant force on this system, what do? You do F1 plus F2. If you want to find the resultant couple, for example, about a certain point O, if I want to find moment about O, what should I do? I should sum the effect of all forces and couples. First, if I take for the forces, I have force F1 and force F2. So here, if I want to do a resultant moment about O, which is of course a vector, okay, I should do for F1, it's R1 factorial F1. This is the moment of F1 about O. For F2, I should take R2 factorial F2. So plus R2 factorial F2, okay, and plus what? Plus the moment couple, because the moment couple, as we said, is a free vector. So even if it's applied at this point, it will have the same effect at O. So I put plus the moment couple. So in general, to have a general rule, the resultant moment is equal to the summation of couples plus the summation of moment of forces about point O. Now, in case we have 2D problem, in a 2D problem, you can say that Frx, you can find the resultant force by finding the x resultant and the y resultant. And to find the moment, because in 2D, when you have all forces in one plane, you will be sure that your moment will be along k, or positive k or negative k. Then you can say that I can calculate the moment as the summation of the algebraic value of couple moments and moment of force. Okay, now we will do some examples to understand this. Okay, in this problem, the street light shown is supported by cable AC. The total weight of the structure is 1,600 Newton, acting at point A, acting at point G, and the tension in the cable is 3,600 Newton. The 200 Newton horizontal force represents the effect of the wind. Replace the force system by an equivalent force and couple acting at B. So here you have a 2D problem. You have several forces acting on your system, okay? And you want to reduce all of these forces into one point. So I want to find the resultant system into point B. To do this, I have two steps. I should find first the resultant force, okay? Then I should do the sum of moments about point B. Now, for the first step, okay, to find the resultant force, we will find the resultant x, the resultant y, and then we do radical fx squared plus fy squared. Okay, so here, this is my x-axis, and this is my y-axis. Okay, so to find my resultant force, so this is x, and this is y. I can say that sum of forces along x equals to, first, I have the 200 for Newton force here is in the positive x direction. So I have plus 200. Now, for this one, it's doing an angle of 45 degrees with x. And if I do the projection, it's in the negative, the projection is in the negative direction. So it is minus 3,600 cosine 45. Okay. In this way, I get sum of x. Now, if I do sum of y, what do I have along y direction? I have the weight that is in the negative direction. So it's minus 1,600. And I have the projection of this force which on y, which is also negative. It's downward. So it's minus 3,600 sine 45. Okay. So now I found my resultant x and resultant y. So I can say that resultant force F resultant is equal to the radical of sum fx squared plus sum fy squared. And what I want to tell you, whatever is the point you want to reduce to, if you want to reduce at B or you want to reduce at A, the resultant force will be the same. Okay, the resultant force is independent of the point. However, the resulting moment will be depending on the point. So if you want to move all your forces and put them at B, you should add a couple equal to the sum of moment about B. If you want to reduce your system at A, you should put your resultant force at A, and you should add the couple of the total moment of forces about A. Because as we said, when we move a force from one point to another, we should add the moment of the force about the new point. So now, since they told me reduce to point B, the second step is to find the sum of moment about B. And I will choose, because it's a 2D problem, okay? My moment is along plus k or minus k. So no need to put it as a vector. I will choose a positive direction, the clockwise or the counterclockwise. So for example, if I select the counterclockwise direction as positive, okay, And I will do now, I will see what are my positive moments, what are my negative moments. Sum of moment about B equals. First, if I look at my forces, I have first the horizontal force, okay? This horizontal force is tending to do a moment about B in which direction? Look, it's trying to rotate about B in the clockwise direction. So it's minus because I choose the counterclockwise as positive. So for this force, it's a negative moment, and I should multiply by the perpendicular distance, which is 4 meters. So I have minus 200 times 4 for this force, okay? Now, for the weight, also the weight, as you can see, is trying to rotate into the clockwise direction, okay? And I should multiply by this distance, which is 1.3, okay? So it's minus 1,600 times 1.3. I still have this force, this one, okay? Now, for this force, to find its moment about B, I have two methods. Or I do the projection from point B to the line of action of the force, and I find the perpendicular. And here I can easily find this distance from, if you want, from geometrical analysis, because I know that the length here of this edge is 5.5 meters, okay? And this is a right triangle, and since the angle here is 45 degrees, so I can say that this distance here is 5.5 times cosine, or here cosine or sine is the same, so times sine 45 degrees, okay? So I can directly multiply the force by this distance, and to know the direction, I can use the right hand rule. If you do the right hand rule, it will be clear for you that this force is doing a counterclockwise moment, so I will count it as positive, okay? Now, the second method to find the moment of this force is to divide it into two components, x and y. And in general, if you have a problem where the distance cannot be found in an easy way, okay, because sometimes the geometry is more complex, the best way is to divide the force into two components, x and y. And it's clear here that the y component will not produce a moment because the y component of your force is passing by point B, okay? So only the x component will produce a moment. And for the x component, if you do the right hand rule, it is clear that it's doing a counterclockwise moment. So all you have to do to find the moment is to multiply the force, which is the projection, which is 3,600 cosine 45, times the distance, which is 5.5. So as you can see, I will get the same result because cosine 45 is equal to sine 45. So the two methods will give me the same result. And now I can replace into my equation, as we said, for sum of moment about B, the 200 force is doing a negative moment, so it's minus 200 times 4. And also the weight is doing a negative moment, so minus 1,600 times 1.5. And for the 3,600 newtons, the moment is plus 3,600 times cosine 45 times 5.5. And you do the calculation. If you get a positive result, this means that your resultant couple is counterclockwise. If you get a negative result, this means that your resultant couple is clockwise. Okay? Any question on this?
Doctor,
Yes.
why did we find in the beginning sum of f on x and sum of y? What are these?
Because you want to find the resultant force. Because look, what is the question? Find the result, replace the force system by an equivalent force and a couple moment. What is the equivalent force? How to find it? The equivalent force is equal to summation of your forces. And to find summation of your forces, you can find sum of forces along X, sum of forces along Y. Then you can find your resultant force. You can find the magnitude and you can find the angle also. If we look here at the solution, so first you find FRX, FRY, you find the magnitude, you will get that FRX and FRY are both negative. So you can say that FR is in the third quadrant. And to determine your angle theta with the horizontal, you do tangent -1 FRY over FRX. In this way, you completely define your resultant force. The second step is to find your resulting couple. So for your resulting couple, as you can see, they choose the positive direction as we did in the counterclockwise direction. When you did the summation, you obtained a positive number along the counterclockwise direction. So your resultant couple is in the counterclockwise. And now you reduce your system to one force, one couple at point B. Okay?
Doctor,
Yes?
equivalent forces, aren't they supposed to have the same resultant force?
Of course. Equivalent systems should have the same resultant force and same resultant moment about any point.
But here you mean like in total?
In total, of course.
Okay.
Okay? Because here, when you did the summation, you find the total force. Okay? So when you have yes.
They're not equal.
Yes, but here, look, you have several forces here, okay? You have several forces acting on your system. So if you want to replace them by one force, this force should be equal to their summation, yes or not?
Yes.
Okay, this is why the resultant force is equal to the summation of the three forces. And to find the summation of the three forces, I decomposed into X and Y. I found sum of X resultant, sum of Y resultant. So I can deduce what is the resultant force of all of these forces. So I can replace these three forces by